last time we started to check and compare the somatoform electron gas model and the actual experimental data for various observables of a simple, say, metal. And the first quantity that we compare is the specific heat, CV, and for metals. And we know that those metals consist of free electrons, and the electrons satisfy this Fermi-Dirac statistics. So this is the Fermi function. Okay? At zero temperature, it is a step-like function, but at finite temperature, part of the electrons right below the Fermi surface will get excited to the states right above the Fermi surface. The amount of the energy window that those excitations occur is about order of kBt, and we can use that information to calculate the internal energy change due to the excited electrons. And the way we calculate this delta U is to calculate first the number of electrons that involve this kind of excitations multiplied by the average kinetic energy for single electron. And the number of electrons is actually the density of states at the Fermi energy multiplied by the width of this windows of order of kBt. And then the average kinetic energy for electrons is again approximately given by kBt. Okay, so you simply just take the product of those two quantities and you get delta U. And you take the differentiation of delta U with respect to temperature, you get a specific heat, which is linearly proportional temperature with a prefactor. So this is just approximated value. The more accurate estimation, calculation for this CV in the free electron somatoform theory is given by this prefactor, pi squared over 3 times density of states and kb squared. So I assign this to you as a homework problem. Okay, so based on the somatoform free electron gas model, you could very easily, evaluate the CV and get this prefactor right. And what about experiments? Well, experiments could actually measure this specific heat, and again, it is a linear function temperature with some prefactor, and the only difference between this experimental results of CV and the predictions made by the free electron somatoform theory is the electron mass. Okay, so the experimental data is actually can be formulated in the same functional form of the T dependence with the modified electron mass. Okay, so remember we talked about the Fermi liquid theory last time. In Fermi liquid, so despite of this Coulomb interaction in those metals, the only thing that changed this free electron prediction is the effective electron mass. Okay, so therefore this m star is not the same as the so-called bare electron mass in the Coulomb interacting electron gas. Okay, so if you take the ratio between this experimental data to the somatoform free theory, and you get a ratio between the effective electron mass and the bare electron mass. And this is something that we could check from our data. And if you look at this ratio for various metals, and you can see that the silver, this ratio is precisely 1, which means that the free electron model is, is very good to describe, this specific heat for this silver. But for lead, for example, this Pb, this ratio is actually 2. Okay, so this is significantly different from what we naively would expect this ratio to be 1, because this, if there's no interactions, then this m star is the same as m. And you could actually check this ratio for various different metals in the periodic table, and you'll see that this ratio is always not 1. Okay, so there's always a deviation from this somatoform theory predictions if you compare this with the experimental data. Okay, so this is the reason why we need to analyze the Coulomb interaction more carefully, and conclusions that the free electron Sommerfeld model is not sufficient. Okay? But how do we treat these Coulomb interactions? So that's the very important issue that we need to address. So let's take a second observables, which is the Pauli spin susceptibility chi, defined as the derivative of this magnetization with respect to the field. If you apply the magnetic field, a very small magnetic field, to the, say, a paramagnetic metal, then you measure the magnetization induced by the small magnetic field. And if you take the ratio of this induced magnetization to the small field, and you define this quantity chi as the spin susceptibility. Okay? So for free electrons, we know that this is the quadratic dispersion of the connecting energy, and it has the many energy levels, and by each level you could populate 2 electrons with opposite spins, and if you apply the field, then there's a Zeeman splitting, which is of the form of B dot S, right? S is the spin of the conduction electrons. Okay, so the spin up electrons will carry different energy with respect to the spin down electron because of the Zeeman splitting. And therefore, this perfect quadratic band got splitted into 2 pieces. Okay, so for spin up electron, the total energy is actually shifted downwards. Okay, by the amount of mu times B, where mu is the magnetic moment, and for spin down electron, this shift is actually upwards. So, but the chemical potential is still the same in equilibrium. So, which means that there are more up spin electrons than the down spin electrons if you apply a small magnetic field, and you can very easily calculate this magnetization. So this is the relation between the electron energy in the presence of the field, or vice versa. Down is shifting up, down, okay? Which means that magnetization is actually the spin moment, the total spin moment, the difference between the spin moment between the upspin species and downspin species. Okay, so let's just take a very rough estimation. And up is given by the average electron density, say minus this quantity, and down plus this quantity. So the net magnetization is given by this. So I only care about the magnitude, mu square B. And as a result, this chi, actually mu square times density of states. So that's the spin susceptibility for ordinary metals at low temperatures, called Pauli spin susceptibility, meaning these electrons satisfy the Pauli principle, and because of the Pauli principle, you get such a susceptibility in the 0 temperature limit. Remember, this Pauli spin susceptibility for ordinary metals is actually a constant, which is proportional to density of states at the Fermi level. And so, but let's look at the comparison between this theory prediction and the experimental observations. From the Sommerfeld free electron model, this chi free is 0.8 for lithium and 0.64 for sodium, but in reality, when you take the data, you get 2 for lithium and for sodium. Okay, so of course for sodium, these 2 numbers are not far away from each other, but for lithium, 0.8 and 2.08 actually the big difference. Okay, so again, this is a deviation. So there are many other examples that you could compare with between this Sommerfeld free electron model and the actual experimental data for the other observables. So the lesson we learned is that we need to treat interaction effect more accurately and more systematically. Okay, so with that, I close the introduction part of the solid state 1. And because of this, we need to treat this or analyze this Coulomb interaction effect in all the solid state systems in a more systematic and accurate way. So as I mentioned many times, that we need to learn how to count the particle number for all the solid state systems, and the way that we count the particle number is to introduce the second quantization formulations. And so let's take a short break. When we come back, we will formally introduce this second quantization for a single particle in a box in quantum mechanics, and then we generalize this to many particle system. So any questions?
那个跟 spin out 跟 spin out 的话，那个 mu 平方为什么会跳出来？
Sorry, there's a mu factor. Here, when we define the magnetization, right? So magnetization is the number of the difference between the number of spin up, spin down electron multiplied by the magnetic moment mu, and there's another mu here in this kinetic energy, so there's mu square. Okay. So if you still have questions, please let me know. I could answer your questions either in class or not in class. So officially, strictly speaking, there's no second quantization. There's only the quantization that we learned in quantum mechanics, namely the first quantization. So the second quantization, this term, is introduced to distinguish this quantization that we are familiar with in quantum mechanics. But this second quantization technique is still based on what we already learned in quantum mechanics, okay, the single particle quantum mechanics. So let's just talk about the single quantum particles confined in a box that we are all familiar with. Suppose this is an electron, and this electron is confined inside the box, and we all learned how to solve this single particle quantum mechanics in a box, right? So we know this quantization in x and y direction, and so on. Okay, so you already learned how to solve the Schrödinger equation. Okay, so and this H is just kinetic energy plus the potential energy. And the potential energy is simply just the infinite potential barrier which defines the wall. Okay, this cubic shape. So you know the eigenstates, which labeled by this alpha, and you know this eigenfunctions, right? But this k alpha is just quantized value, and this nx, n1, and nz are simply this integer numbers. Okay, so far, so good. This is just a single particle quantum mechanics, and this alpha labels the eigenstate. For example, this alpha labels the, for example, this ground state or first excited state, and so on and so forth. And there's the orthonormal condition, orthogonal and normalization condition for all these eigenfunctions. Suppose there are two eigenstates represented by the two wave functions u alpha and u alpha prime. And if you take the overlap integral between these two states, and you get a normalized factor, delta alpha alpha prime, which is 1 if alpha is the same as alpha prime, and 0 if alpha is different from alpha prime. So this is well known in quantum mechanics, right? So let me just play some trick and mathematical manipulations of this orthonormal conditions and all the other representation in quantum mechanics. Namely, we try to discretize this integral in a finite size system with many finite lattice points. So suppose this is my cube or my box, and I can simply just discretize this box in terms of many small little box or little cube, which I call this delta omega. So in the previous standard formulation, this wave functions or eigenfunctions as function of special vector r is continuous. So this is a continuous function of position vector r. So now I play some trick. I want to actually discretize this continuous eigenstates or eigenfunctions in terms of a discretized representation of this wave functions. And this discretized version of the continuous wave function can be defined through a matrix, either the column matrix or a row matrix, then we could adopt this Dirac notation, okay, to rewrite this discretized eigenstates or wave functions in terms of the matrix product. Okay, so that's the starting point of the second quantization. So let me just discretize this. Suppose this is the ith little cube, and I could discretize this whole region in terms of this, little site I with a volume delta omega. So now let's rewrite this, normalization condition in terms of discretized variables, which is delta omega. Instead of integration, you sum over those discretized values. Namely, you could define your eigenstates or eigenfunctions in such a discretized lattice. Okay, so it's like that, instead of using a continuous variable, so I now do it a different way. So let me just discretize this real space vector R in terms of many, many lattice points, and there's no curve connecting those isolated points. So I can simply just pretend that if I connect all these discretized points, I go back to the original, wave function in the continuous fashion. But instead of using continuous representation, I rather use the discretized version. So they are all equivalent as long as the points, the number of points goes to infinity, then there's no difference at all, right? So let's do it. So if I discretize this, real space variables in terms of a little cube or little volume, then the continuous integration becomes a sum of discrete values, right, of u alpha star and u alpha prime. So now I keep manipulating this formula in terms of a very useful representation, which is the Dirac notation. So I could just consider those u alpha different little cube as a matrix element of a column or row matrix, and this discrete sum of this u star and u star alpha and the u alpha prime is simply just a matrix product between this row matrix and column matrix with the matrix element precisely this u star alpha 1 star alpha Rn u alpha prime R1. Okay, so if you simply just take the matrix product between this row matrix and the column matrix, and you go back to this discrete summation of this u star and u. All right? So this is 1 by n called row matrix, and this is n by 1 column matrix. So if you multiply 1 by n matrix by n by 1 matrix, you get 1 by 1 matrix, which is a number, okay, which is exactly this. So I did not do anything. I simply rewrite this discrete summation and re-express this in terms of a matrix product between the row and column matrix. But the great simplifications could come if we define this or identify this kind of matrix product between the row matrix and the column matrix is nothing but the Dirac state. So this is Dirac broad state, and this is Dirac cascade. So I assume that everyone should be familiar with the Dirac notation, right? The broad state in terms of the matrix is just a row matrix, and the cascade in the Dirac notation is the column matrix. Instead of using this matrix and matrix elements, which is very troublesome, why not we simply just use a very simple notation invented by Dirac, which is the Dirac broad state and cascade. So now let's just rewrite this orthonormal condition in the Dirac notation. Okay, so the orthonormal condition now reduces to this very simple equation, which is this overlap between the Dirac cascade and broad state, and the cascade is alpha prime, the broad state alpha, which is given by this delta function. Okay, so this lengthy, troublesome expression here reduces to just a couple of symbols in a very short line. Okay, so we could greatly simplify the orthonormal condition if I use this Dirac formulation. But this is just a starting point because we could take advantage of this simple Dirac notation. This allows us to redefine a quantum mechanical operator. So any wave function in quantum mechanics, which I call this phi, could be expressed in terms of this Dirac cascade alpha and form the linear combinations of all the Dirac states, and you could come up with any arbitrary quantum state in Dirac notation. This is called this Fourier decomposition of a Dirac state, right? So the Dirac state, any arbitrary Dirac state, is a linear combinations of orthogonal and normalized eigenstate. But I could rewrite this, standard definition for, the Fourier decomposition in terms of, this Dirac notation, because I know that this operator, which is resolution of identity operator 1, in the Dirac notation, it is simply this kind of a matrix product, or the product between the Dirac cascade and Brat state. Why? Because in the matrix representation of the identity operator, it is nothing but 1 along the diagonal directions, but 0 otherwise. Okay, so this is identity operator. So when you multiply identity operator to any operator, it's like 1. Okay, so 1 times anything is anything, and you could understand this kind of identity operator in terms of the matrix product between this Dirac cascade, which is the n by 1 column matrix, multiplied by a Dirac Brat state, which is n by 1, right? So this is n by 1 times 1 by n, which is n by n. From your linear algebra, you know that if I multiply this column matrix by a Brat matrix, this will lead to an n by n matrix. Okay? So don't get confused. The key point is how you place the cascade and Brat state. Is the cascade on the left or on the right? So here, the cascade is on the right and the Brat state on the left, and therefore it is 1 by n by 1, which is 1 by 1. But if you simply switch the order between the Brat state and the cascade, you get n by 1 times 1 by n, which is n by n. If you switch the Dirac cascade and Brat state, you get a completely different thing. Okay, so on the one hand, this kind of arrangement of a Dirac cascade and Brat state gives you a number, which is a 1 by 1 matrix. But if you switch the order, it is not giving you a number, but a matrix. Okay, so I hope everyone should distinguish this kind of matrix product and distinguish between a number and a matrix. A number is just a single valued quantity, but the matrix contains n times n matrix elements. Right? So if you simply just multiply this two, you are exactly recovering this identity operator, and therefore I could insert this identity operator anywhere, anytime I want, because this is simply just 1. Okay? However, if I do so, I will get benefit. What is the benefit? Well, the benefit is that I could encircle this in a different way if I don't encircle this identity matrix. Instead, if I simply just focus on this, and if you compare this to expression, you immediately see that this coefficient C alpha is nothing but this matrix product between the Dirac Brat state alpha and cascade phi. So that is again quantum mechanics. There's nothing fancy about this. It's simply just a Dirac notation. So we are taking advantage of such a Dirac notation, and we rewrite everything in terms of this Dirac Brat state and cascade and the matrix product. It's just a review of quantum mechanics, nothing more. Okay? But you will see something different just now. So if you do so, then you could rewrite this potential operator in terms of a Dirac Brat state and cascade, and you could define what we call this creation and destruction operator. So let's just rewrite this kind of standard definition in quantum mechanics in the, in the Schrödinger picture. If I try to evaluate this kind of expression value of this potential operator V, and this is what we should do in ordinary quantum mechanics in the Schrödinger picture. But now I could rewrite this in terms of the matrix product as I defined over there. So this is just some, overlap between this U alpha state and U alpha prime multiplied by this V of R. Okay, so in quantum mechanics, it's just a number, but this, in the Dirac notation, is the matrix element, because you could define your operator in the Dirac notation. Okay, so suppose this is your quantum mechanical operator for a single particle potential, for example, this V hat, and we could multiply this by identity matrix I, which I already defined, right? So let me just do this. So this is, I could multiply this anywhere I want, anytime I like. So this is alpha prime cat, and alpha prime broad, and V. And I can also insert this resolution of identity matrix on the right. So I get, again, alpha double prime, right? So this is identity matrix, and this is, again, identity matrix. So I did not change anything. I simply insert this identity matrix on the left and right side of operator V. But let me just, instead of encircling this identity matrix, I simply just try to encircle this stuff defined within the blue region. Okay, so let me just put the summation right out front, and let me just prime alpha double prime and alpha prime V alpha double prime. Okay, so the stuff inside the blue circle here is nothing but the matrix element of this operator V. And what about this? The strange combination of a Dirac Castet on the left and Dirac brush on the right. Well, this is operator. Remember, the Dirac Castet is the matrix with n by 1 matrix, and the Dirac brush state is actually 1 by n. So this is n by 1 by 1 by n, which is n by n. Whenever you could express this term in terms of matrix, this is, of course, the operator. Let's just rewrite this fancy expressions in terms of creation and destruction operator. So let me just rewrite this. Okay, so I can redefine this, re-express this quantum mechanical operator V in terms of matrix element V alpha prime alpha double prime multiplied by an operator. So let's try to see what this means, this operator. Okay, so if I encircle this operator, I would like to see what this does to the system or to the operator. So let's just pretend that we don't know what this means. So because we know that this is operator, and let's just try to act this operator onto the eigenstate alpha and see what it gives us. So suppose this is the operator in the Dirac notation and acting on this another Dirac Castet, which I call this alpha. And let's just do this algebra. So if you simply just neglect this orange curve and look at this, the blue stuff here, and what this tells us, this is nothing but alpha prime, but you get another overlap or matrix element or matrix product between this Dirac brush on the left and cast on the right. This is 1 by 1, which is a number. What this number tells you? Well, this is nothing but delta function, right? From the orthonormal condition, this is nothing but delta function. So let's just write down the final answer, and this gives you alpha prime Castet if alpha is the same as alpha double prime, and 0 if alpha is not the same as alpha double prime, right? But we could reinterpret this operation in terms of creation and destruction of a particle. So how so? Let's look at the effect of this operator. So this operator, which I call this A operator, acting on A alpha prime, alpha double prime, acting on alpha gives you alpha prime if alpha is the same as alpha double prime, and 0 if they are not the same. So let me finish this. So this operator A, defined inside the red box, actually is made of a state alpha prime, alpha double prime. But when you look at the resulting state, when this is, this acts on the state alpha, it only gives you alpha prime or 0. Okay, so in a way, this operator A actually destroys the state alpha double prime, but create alpha prime. So if you act this operator onto this any arbitrary eigenstate alpha, this operator reports the results that can only be alpha prime. In a way, this operator destroys the original alpha double prime state and actually creates alpha prime. So this is the lesson we learned, that this operator destroys alpha double prime but creates alpha prime. Okay, so let me just define my vacuum 0, which is the empty state, a state with no particles. And I could rewrite this operator A in terms of the vacuum state, right? So again, this vacuum state still are normalized and orthogonal states. So 0 states, say the brass on the left, and multiply with cascade of vacuum state on the right. This is simply just 1. But again, if I rewrite this in terms of this vacuum state in the middle, then I can encircle this in a different way, like this. And I could define this as, say, A alpha prime 0 and A 0 alpha double prime. Or symbolically, this is called C dagger alpha prime, and this is called C alpha double prime. Okay, so let me just reinterpret this operator. So using the same interpretation that we found over here for A alpha prime alpha double prime, here we could interpret this A alpha prime 0 as you destroyed a vacuum and you create alpha prime state, right? So you destroyed a vacuum, but you create alpha prime. Okay, so what do we mean by you destroy the vacuum, but you create alpha prime? Which means that you create a particle out of nothing, right? So you destroy the nothing state, which is empty state, but you create another single particle state alpha prime. So you create a particle. So let's look at the other operator over here. You already have this initial state alpha double prime, which is a single particle state, and you destroy that alpha double prime, but you create nothing. You create empty state. So this operator tells you that you destroyed a single particle state alpha double prime, but you create an empty state. So this means that you destroy the particle and you create an empty state, which means that you destroy the particle. Okay, so let's stop here, and we will describe such an operation on Wednesday. So this is something new that you should be familiar with, but it takes time. Okay, so I will try to explain this on Wednesday once more.